Hey, welcome to another episode of Proof Pilot. We are going to talk about why, in fact, the subspace topology is unique. So we discussed that each of these new topologies have some unique property. They have a characteristic property that only them and them is going to satisfy them. So here is why. Uh, Suppose that S is a subset of topological space X. The subspace topology on S is the unique topology for which the characteristic property holds. That's just a formal statement of what I just said. And in order to prove this, there is a statement that you need to prove. Then we are going to get to that. I can't remember if I proved this, but I will post it on the YouTube channel, the proof of this. But I'm going to use it right now. So this thing right here says if you have two topological spaces and F is a bijective map, then F is a homomorphism if the topology on if the image of the topology becomes equal to the other topology. So here it should be T2. And in other sense, if U is a member of your first topology, then F of U is going to be the member of the second topology. So the idea here is that we suppose that there are two topologies that satisfy the characteristic property. And we are going to show that these two things are actually the same. So one thing that comes into mind is using the identity function. And the other thing is this exercise. So if I have an identity function which is a homeomorphism, then I can say that these two things are in fact equal. So let's just see what happens. One thing about the subspace topology was that it satisfies the characteristic property. So if I have two topology that satisfy this characteristic, then let's just write that diagram that we had in the past again for these two topologies, and let's see what happens. So this was our space, and this was the subspace topology. And here we have the identity map. It's from G to S here. Then this is the inclusion map, and the inclusion map was continuous. And here it will be the composition of the inclusion map and the identity. Now for the other one, here is going to be the subspace topology, and this was the topology that we are claiming is different, but in fact it's not. And here is going to be my space, and this is the inclusion map, and here is the composition of two. So if I show that the identity function is continuous and the inverse of the identity function is continuous, since this is between two spaces that have the same size and same members, then this thing will be a homeomorphism, and we can say that the topology on your subspace topology is the same as the topology that you're claiming that's not subspace topology. And since this is a homeomorphism and it's an identity map, then in fact these two things are equal. So we had the characteristic property which said if this thing is continuous, then so is this. Now we have only to prove that these two things are continuous. Then we can claim that these things are continuous, and just note that these two actually are the inverse of each other. So these things are inverse of each other. So we have an identity map which is continuous, and the inverse of the identity map is continuous. So we can say we have a homeomorphism. Now all we have to do is to say that the composition of the inclusion map and the identity is continuous. And this is actually the nice part, because we know that the inclusion map is continuous, and just look what this thing is equal to. It's just equal to the inclusion map on the other side, and this is continuous, so this is equal to the inclusion map, and this thing is continuous. And we know that the inclusion map on this side is also continuous. So the identity map has no choice to other than be continuous. So this thing is also continuous. And again, we have the same thing over here. And now we can say that these two topologies are in fact the same. This was just such a beautiful proof. If you like this proof, please comment and subscribe. See you in the next one.